Okay, class. So this is going to be a review on all the stuff we've covered so far in energy. None of this should be new, so we're just going to go over kind of some of the more basic concepts and then go into some problems to kind of facilitate us being ready for the upcoming quiz. So these are the following quantities that we've so far looked at. The first of which being energy, the fuel. We've measured that in joules, calories, BTUs, and kilowatt hours. We've then looked at power, which is energy use per second. And that we've measured in watts, and with that we've tagged on megawatts, kilowatts, gigawatts, as well as we've looked at it as a joule per second. Wrapping those two together, we've looked at time. We've looked at that in this unit as well as many of the other units, but time is essentially just how long something takes. And we measure that in seconds, hours, minutes, years, days, anything of that nature. Current, which is a fairly newer concept, is how quickly electrons flow. And we measure that in amperes, also known as just amps. Voltage, lastly, also a newer concept, is the drive that pushes electrons through a wire. And as the name kind of entails, we measure this in volts. Looking at our conversions, we've so far in this energy unit looked at just a couple of these metric conversions. These were previously level 1 conversions, but now as we've gotten more used to them, we're more comfortable with them. This is something that's expected of everyone. So we've looked at a watt, but as well as a kilowatt, a megawatt, and a gigawatt. So a kilowatt has 1,000 watts. A megawatt has 1,000,000 watts. And a gigawatt has 1,000,000,000 watts. We can write them as you see them here on the page, but remember we could also use scientific notation. So a kilowatt would be 1 times 10 to the third, because as you see here there are 3 zeros. A megawatt could be 1 times 10 to the 6th, because as you can see here there are 6 zeros. And then a gigawatt could be written as 1 times 10 to the 9th, as you can see here by the 9 zeros. We've looked at, however, not just metric conversions, but just, any general energy conversion, because we're not only going to be looking at metric. Here we have a kilowatt hour, kind of our base energy unit that we've used for the most part in this class. And one of these kilowatt hours has 3,600,000 joules. There are a lot more. A kilowatt hour is a pretty big unit of energy, so we're going to have a lot of joules. Likewise, 1 kilowatt hour is equal to 860,000 calories. Again, showing just how big a kilowatt hour really is. And then lastly, 1 kilowatt hour is equal to 3,412 BTUs. Looking away from just the concepts, we've broken down this first chunk of the energy unit into 3 different equations. So we're going to look into each of these equations individually and see what concepts kind of grew about them. But our first equation was that energy is equal to power times time. Our second was that power is equal to current times voltage. And then lastly, we looked at efficiency, being what was used over what was supplied. We're going to first hone in on this energy equals power times time. So we went over a slide something like this in class. So which car would run out of gasoline first, and why? If we look at both of them, and we put in 1 gallon of gas into both these cars, the Subaru Impreza, which is the car I drive, and the Ferrari, which is definitely not the car I drive, we would be putting 1 gallon of gas into both, but the Subaru Impreza has 30 miles to the gallon. The Ferrari has 15 miles to the gallon. We put the same amount of energy into both, the gasoline. But how much we're getting out of it is different. So the amount of energy per second is different. If we kind of clock both of these cars, we'd be getting a whole lot more output from the Subaru Impreza. It's going to be going much further just on the use of that gas. The Ferrari is going to burn it much quicker. That idea between the gas and how quickly they're using it is the basic difference between power and energy. And if we look at kind of these quantities together, here we have energy. We're going to be looking at it most typically in a kilowatt hour. We can think of that as, the kilowatt part being power and the hour part being time. A kilowatt hour, power times time. But we can also look at this through any of the units we've looked at. So a watt times a watt second, that's another way we could look at energy. And that's also known as a joule. And we can even throw in some funky units. We can put a megawatt year. Well, this doesn't really have a name, but a megawatt year is a unit of energy because a megawatt is a unit of power and a year is a unit of time. So let's try this in a problem. How many kilowatt hours does it take to keep a 2 kilowatt dishwasher running for 3 hours? So you should pause the video at this time and give this problem a try. Okay, hopefully you have an answer, so let's look at it. We should have gotten, that as said in the problem, that we have 2 kilowatt hours of power and we have 3 hours of time. We have 2 kilowatts of power and 3 hours of time. So if we plug those in and multiply them together, 2 times 3, that's going to be 6 kilowatt hours of energy. Let's look at another problem. How many kilowatt hours does it take to run your 2,000 watt oven an hour per day, 3 days a week, for a month? This one's a little trickier. Let's read it over a couple of times. Give this problem a try and pause the video. I'll be giving the answers once you unpause the video. Okay, so for this first one, we're going to look at power, and the problem's asking for it in kilowatt hours. So we have to take our watts and convert that first to kilowatts. So we have 2,000 watts. There are 1,000 watts in a kilowatt. So we convert that so that 2,000 then becomes 2 kilowatts. So we can plug that in to where we have power. The time here becomes kind of tricky. So it's saying that we have the oven on for 1 hour a day. So we're starting out with 1 hour. And then we operate that 3 days a week for a month. So we're working at it with 3 days a week, so we put that there. And then 4 weeks are in a month. So that's going to cancel the weeks in the 3 days a week. Weeks cancels out. And we then have finally our units of hours, because that's what we want. So we have to look at kind of how many of these hours we're working with. And since here we're working with it 3 days a week for a month, we have to figure out, okay, how many hours are we dealing with? Because what we want in the end is hours, because we want it to be a kilowatt hour. So we have our total hours being 12, our total power being 2 kilowatts. We multiply those two together, 2 times 12, and we get 24 kilowatt hours. We've also looked at the parallels between this equation that we've just worked with in a couple of examples, as well as how it's similar to our change in position equation, which was also similar to our area equation. So if we look at kind of the parallels between all three of these equations, we see that energy is kind of like our change in position, which was also kind of like area. Power is kind of like velocity, which is kind of like length in the area equation. Time, similar to time in our position equation here. And then lastly, kind of similar to width. So energy equals power times time is in a weird way kind of like area is equal to length times width. So we can look at this graphically and really focus in on this idea of the area being analogous to energy. So here, just like before, where we had a graph with velocity on the y-axis and time on the x, and the area under the curve being the change in position, if we look at a graph where power is on the y-axis and time is on the x-axis, the area underneath that curve is energy. And as we saw in our lab before, we can manipulate this energy in various different ways. We can have more power, less time. We can have more time, less power. These are all ways in which we can control the amount of energy we're working with, whether it be a microwave, a toaster, a hair dryer. All of these different appliances manipulate either the power or the time in order to have different energy outputs. Okay, let's look at our second equation that we looked at. Power is equal to current times voltage. With these, we are working with wires and electricity running through these wires. And the first concept we looked at was the idea of current. This is how quickly the electrons in the wire are moving. So if we have more electrons moving through the wire, we're going to have more current. It's kind of like the idea of a river. When we think of water flowing, if the current is strong, we have a lot of water running through that river. But if the current is weak, we don't have that much water. We can think of the water and the electrons as being kind of like the same thing here. If it's moving fast, it's high. If it's moving more slowly, we don't have that much current. And one way we can look at this is through the ideas of fuses and circuit breakers. You guys have probably heard of these. They're in all of your homes. And these are regulators in our homes that if we ever have too much current, so too many electrons running through the wires in our homes, they actually turn off the power so that the wire doesn't get too hot and break anything in your house. So if the current ever gets too high, these have mechanisms to stop them from damaging things in your home. Volts is the other concept we looked at. We can think of this as the drive that pushes these electrons from one end of the wire to the other. One easy way to think about this is that we can think of one side of the current being kind of negative, where the other side is kind of positive. And if electrons are negatively charged, they're going to move away from the negative side and towards the positive side, because opposites attract. If the difference in these charges on the ends are greater, so if there are a lot of negative, we can think of it as a strong negative charge on one end and a strong positive charge on the other, these electrons are going to be pushed really rapidly with a lot of force to the other end. But if the difference is not that big, so if we don't have that many negatively charged ends on one side and not that many positively charged ends on the other, they're not going to be driven that much. So if we have a bigger difference, we're going to have more voltage. And with voltage, we've talked a little bit about what we can expect from voltage. If we're dealing with any power outlet in the United States, as we saw in the lab, we're always going to have 120 volts as long as we're here in the United States. We won't always have 120 volts though if we plug it, let's say, into a battery. Different batteries have different volts as well. There are 9-volt batteries, 12-volt batteries, and depending on which batteries we use, we'll have, different volts. As well as if we went to a different country, for example, in Europe, their voltage, if you were to plug into the wall, is somewhere around 220 volts. And this is why we need a converter whenever we go to a different country. It's not just because of the shape of our outlets, but also because of the voltage that these different countries run at. But here in the United States, we run at 120 volts. So it can be assumed that in any problem where we're plugging into a wall here in the United States, and I don't put a voltage, that we're running at these 120 volts. So let's actually look at this and apply it in a problem. So what is the power in watts it takes to have 0.5 amps of current run on an 8-volt battery? So I want you guys to pause the video at this time and give this problem a try. Okay, what is the power in watts it takes to have 0.5 amps of current run on an 8-volt battery? So here we can look at the answers. We have 0.5 amps, 1.5 volts, and 4 watts.